In this video, we'll talk about the properties of logarithmic functions. All of the properties of logarithms are derived from the corresponding properties from exponential functions. The main properties that we will use are the algebraic properties and the cancellation laws. The first algebraic property tells us that the log base b of a product x times y is equal to the sum log base b of x plus log base b of y. Logarithms turn products into sums. Similarly, logarithms turn division into subtraction. So log base b of x divided by y is equal to the difference log base b of x minus log base b of y. The next property is a special case of the first one, or not the first one, but the previous one. Log base b of 1 over y is the opposite of log y. That should be log base b. So log base b of 1 over y is equal to the opposite of log base b of y. This is really the previous, just with x is equal to 1. So log base b of 1 over y is equal to log base b of 1 minus log base b of y. And log base b of 1 is equal to 0. That's actually a property over here. But this one goes away, and you're just left with the opposite of log base b of y. The next property is log base b of x to the r is equal to r times log base b of x. So this property of logarithms tells us that we can take the exponent out of the exponent and put it in front of the logarithm. This is a very useful property when you want to solve an expression or an equation for a variable which is in an exponent. If you want to get it out of the exponent, you want to use a logarithm. We also have cancellation laws. These are based on the fact that the logarithm base b is the inverse of the exponential with base b. So that's really what this is saying. B to the log base b of x is equal to x. Whatever it is that log base b does to x, the exponential base b undoes it and you get x back. That's why we call it cancellation law, because the b to the log b cancels out and just gives you x. Similarly, we have log base b of the exponential b to the x is x. So the exponential base b takes x to some number, and then log base b just sends it back to x. The next rule is really just a restatement of, or a special case of, the previous. So log base b of b is equal to 1. That's because b is equal to b to the 1, so this is log base b of b to the 1 power. So just using the previous with x equals to 1 will give you 1. The same is true of the last property we have written here. That's why these are written underneath the cancellation laws, because they're a special case of the cancellation law. Log base b of 1 is the same as b to the 0. So log base b of b to the 0 is going to be 0. So again, that's this law with x equals 0. Let's do some examples now where we make use of the properties of the logarithm. So example 1. For the following, use the properties of logarithms to expand each logarithm as much as possible. So you can see here we have a logarithm of a thing. But that thing is quite complicated. What we want to do is rewrite each expression as a sum, difference, or product of logarithmic functions where the arguments of the logarithms are all linear terms. So linear means degree 1, so it's an mx plus b kind of term. So we want to write all of our terms like that. So we have this log of something complicated, and we want to write it as a sum or difference of much simpler logarithmic terms, where the highest degree on x is 1. That's our goal. Okay, let's see if we can make that happen. So here we have the logarithm of a quotient. So logarithms turn quotients into subtraction. So this is the same as log. So this is log without a base written. So it's understood that that's log base 10, the common logarithm. So this is log base 10 of the numerator, 3x cubed minus 12x minus log of the denominator, x squared plus 6x plus 5. But each one of these arguments can be factored. So let's do that. Let's factor them. So this is log of 3 times, well, let's take out an x as well. 3x times x squared minus, and 12 divided by 3 is 4. So 3x times x squared minus 4 minus the logarithm of, and I think we can factor this one too. So this is x plus 5 times x plus 1. So 5 times 1 is 5, and 5 plus 1 is 6. Okay, so now we have log, again, of a product. Actually, there are 3 products here. Here we have log of a product. So let's use the properties of logarithms that turn products into addition. So this is going to be log of 3 plus log of x plus log of x squared minus 4. Actually, we can factor that one too, so we'll do that in a second. Minus log of x plus 5, and then minus log of x plus 1. There's a minus here. So these are 2 terms, so it's log of x plus 5 plus log of x plus 1. But we're subtracting both of them. So this minus sign is that minus sign, but it's also that minus sign. So don't forget that. So this term right here, this term is log of x plus 5 plus log of x plus 1. It's all of that. But we're subtracting all of this, so we have to subtract each term. So you subtract each term. Now we're almost done, but we can actually factor this term too. X squared minus 4, that's the difference of squares, so that's x plus 2 times x minus 2. So that tells us that we have log 3 plus log x plus log of a product. So we'll write that as log of x plus 2 plus log of x minus 2 minus log x plus 5 minus log of x plus 1. Okay, so we've expanded this as much as possible. So that's what was the instructions. Expand as much as possible. If we couldn't break all of these down into a product of linear terms, like this numerator was the product of, it had all of its factors were linear. This constant is also linear because the degree is less than 1, less than or equal to 1. So a linear term, like if we have 3, that's 0x plus 3. So that still counts as a linear term, even though it's constant. The denominator was also factorable into a product of linear factors. It's only because we could factor these things completely that we were able to write it like this. Let's do another example. Here we go, log base 2 of x plus 1 times x squared plus 1 divided by x squared minus 9 divided by x squared minus x minus 6. So that's in the denominator as well. This x squared plus 1 is not factorable, at least not over the real numbers. So we actually can't follow the instructions to make things to logarithms of linear terms because of this. But we can still do it as much as possible. Let's just factor everything completely. Let's just do it over here. So this is log base 2 of, now the numerator, you can't do anything to the numerator, x plus 1 times x squared plus 1. So this x squared plus 1, we can't factor that anymore. So the denominator, x squared minus 9, that's the difference of squares, so we can write that as x plus 3 times x minus 3. So x minus 9 is both of these terms right here. And now we can factor this one, at least I think we can probably factor it. So that looks to me like x gives me x squared, and then we have a 3 and a 2. That gives me 6. Needs to be a negative in front of the 3. So negative 3 times 2 gives me the negative 6, but we need a negative there, so that's why the negative sign had to go in front of the bigger one. Negative 3 plus 2 gives me a negative 1. Okay, so now it's factored completely. So the numerator is factored completely and the denominator is factored completely. So now we're going to use the property of logarithms, so this is log base 2, that turns quotients into subtraction. So this is going to be x plus 1 times x squared plus 1 minus log base 2 of the denominator, which is x plus 3 times x minus 3 times another x minus 3, but we'll just leave them factored like that, x plus 2. Because we're going to separate it out in a second anyway. Okay, so logarithm of a fraction is the log of the top minus the log of the bottom. Log of the top minus the log of the bottom. And now we're going to convert all of these products into sums here too. So this is log base 2 of x plus 1 plus log base 2 of x squared plus 1. So that's the first one. Let me just put it in parentheses like that. Like that. And then it's going to be minus, and I'm going to put everything else in parentheses as well, or brackets. So we're going to ignore this minus sign for the time being. So this minus sign is that minus sign, but I'm just going to leave it outside of what I'm doing, as outside of the bracket. Now inside here, I'm just going to guess where this ends. Inside here, I'm going to expand the logarithm base 2 of this product. I'm going to turn all of these products into sums. Okay, so this is going to be log base 2 of x plus 3 plus log base 2 of x minus 3 plus log base 2 of x minus 3 plus log base 2 of x plus 2. So now what I want to do is I want to subtract all of these. So this is going to be log base 2 of x plus 1 plus log base 2 of x squared plus 1. And now we just subtract every one of these. So it's going to be minus log base 2 of x plus 3 minus, well, here we actually have two of these terms, so let's just group them together. So it's going to be 2 log base 2 of x minus 3 minus log base 2 of x plus 2. So this minus sign right there is the same as all of these minus signs. And these two we combined like that. We weren't able to expand this entirely into logarithms of linear terms because of this term right here, x squared plus 1. That doesn't factor. But we were able to expand it into terms that were as simple as possible. Let's do another one. All right. The natural logarithm of, well, this is a rather complicated expression, x cubed y squared z to the 5, all divided by x minus 3 raised to the 4 and x squared plus 4 raised to the 4. Again, notice that we have this sum of squares. We're not going to be able to factor this, but that's okay. So let's just go ahead and use the logarithm properties. So this will be the natural logarithm of the numerator, x cubed y squared z to the 5, minus the logarithm, the natural logarithm of the denominator, which is x minus 3 to the 4 times x squared plus 4 to the 4, like so. Alright, so what we're going to do now is we're going to use the property of logarithms that turns products into addition. So this will be ln of x cubed plus ln of y squared plus ln of z to the 5. And that's our first logarithmic term expanded. And it's going to be minus our second logarithmic term. So I'll put a bracket there. So this will be ln of x minus 3 to the 4 plus ln of x squared plus 4, and we're going to raise that to the 4, like so. So now we can use the property of logarithms that allows you to take the exponents out. So all of these exponents, we can just take these out. We can take out, let me just change the color here. We can take out all of these exponents and bring them in front of the logarithms. We can do that for every one of these. The 4 comes out here. That 4 comes out here. So let's just go ahead and do that now. So we're going to have 3 times ln of x plus 2 times ln of y plus 5 times ln of z. And from this we're going to subtract 4 times ln of x minus 3 plus 4 times ln of x squared plus 4. So you'll notice sometimes I write ln in cursive and sometimes in script, and not cursive, that is. Okay, so now we just need to distribute that minus sign. So it's 3 ln x plus 2 ln y plus 5 ln z minus 4 ln x minus 3 minus 4 ln x squared plus 4. So this minus sign right here is the same as that one, and then it's both of these. This is expanded as much as possible because we can't factor this x squared plus 4. For this example, we're going to do the opposite. So for each of the following, we're going to condense into a single logarithm if possible. So we start out with several logarithms and we're going to combine them. So let's do that. So this is log without a subscript, so that's understood to be log base 10. So I'm going to write this as, the first thing I'm going to do is I'm going to write this 3 log 2 is log of 2 cubed. So I'm doing the opposite of what I was doing before. I'm taking that 3 that's in front of the logarithm and I'm putting it into the exponent. Plus log 3 minus log 7. I could do something to that, but I just didn't. Okay, 2 cubed is 8, so this is log 8 plus log 3 minus log 7. So now I'm going to combine these two. So this is log of 8 plus log of 3, that's log of 8 times 3, minus log of 7. Okay, so 8 times 3 is 24. So this is log of 24 minus log of 7, which is equal to log of 24 divided by 7. And that's our answer. Let's do the same thing here. Now we have just a few more terms to worry about. And we have some x's instead of just numbers, but that's okay. We just treat them like numbers. So this is going to be, let's just leave the 3 out here for now. So the first thing I'm going to do is I'm going to take that 4 and I'm going to put it into the exponent here. So this is going to be log x to the 4. And this is minus log x minus 3 minus log of 5x minus 2. So both of these, this x minus 3 and that 5x minus 2, these are going to end up in the denominator because of that minus sign. So we could actually rewrite this. So this is going to be 3 times, I'm going to just leave the 3 out there for now. So this is going to be log of x to the 4, and I'm going to factor out that minus sign. So it's going to be log x minus 3 plus log 5x minus 2. So these two minus signs are the same as that minus sign. If I distribute this minus sign through these parentheses, you'll get those minus signs. So now these are a sum of logs, so I can write that as a logarithm of a product. Like so. So now I have 3 times log x to the 4 minus log of this product. X minus 3 times 5x minus 2. Okay, now I have the difference of two logarithms, so I can write that as the logarithm of a quotient. So the difference of two logarithms is the logarithm of a quotient. So this is 3 times log of x to the 4 divided by x minus 3 times 5x minus 2. And now finally we're going to take this 3 and we're going to put it inside as an exponent on this thing here, right here. It's going to go right here actually. So it's going to go right there. So this will be equal to log of, so it's going to be x to the 4 over x minus 3 times 5x minus 2, and all of that raised to the 3. So the property tells us that if you have an exponent, if you have the logarithm of something raised to the 3, you can take the 3 outside. Now here I'm just going backwards, and I'm putting the 3 back inside as an exponent. So now what I want to do is I just want to cube everything inside these parentheses here. So this is going to be log of x to the 4 cubed is x to the 12 over x minus 3 cubed times 5x minus 2 cubed. So this x to the 4, remember x to the 4, if you raise that to the 3, that's x to the 4th raised to a 3, that's like multiplying the exponents together, so that's x to the 12. So that's where that x to the 12 comes from. So now what we've done is we've taken all of these logarithms and we've combined them into just one logarithm. Logarithm of a complicated expression, but it's just one logarithm. Let's do another one, this time with the natural logarithm, but it's the same basic idea. So this is 1/2 times, so this is ln, I'm just going to leave this one alone, plus, but now I'm going to take this 4 and I'm going to put it in the exponent here. Let me just try a little bit harder. I'm going to put it right there. That's where it's going to go. And this 3 is going to go inside right there. So let's just do that. So it's ln of y plus 3 to the 4th minus ln z to the 3 minus ln z minus 4. Okay. So this is 1/2. So what I can do is I can combine these two. It's the sum of logarithms, so I can turn that into the logarithm of a product. So this will be ln of x plus 1 times y plus 3 to the 4th, like that. And now here I have a minus in front of both of these, so let's subtract that. So that's minus ln z to the 3 plus ln z minus 4. And all of this is being multiplied by 1/2. So maybe I should use parentheses here just to keep it from getting too confusing, like that. Okay, so there's a 1/2 in front. We'll deal with that at the end. So there's a bracket, and this is an open bracket, and this is a closed bracket. So this, might as well, since I'm accidentally using gray, I might as well change the highlighter. So these minus signs I factored out, and that's that minus sign, like so. So the reason I did that, the reason I took out that minus sign is so it was easier to see how to combine these two. So this is the sum of two logarithms. So that means it's the logarithm of a product. So this is going to be, equal to 1/2 ln And I'm just going to leave this alone right now. Y plus 3 raised to the 4 minus, and I'm going to combine these two logarithms. So this becomes z to the 3 times z minus 4, like so. Now I have the difference of two logarithms. The difference of two logarithms, that turns into the logarithm of a quotient. So this is 1/2 times ln of a quotient. So it's x plus 1 times y plus 3 raised to the 4, and all of this is divided by z to the 3 times z minus 4, like that. And the next thing we do is we take that 1/2 and we put it inside. So we're going to take this 1/2 and we're going to put it right there. So we'll have a 1/2 here, or a square root if you prefer. So this will be equal to ln of x plus 1 y plus 3 to the 4 divided by z to the 3 z minus 4. And all of this is going to be raised to the 1/2 power, which we could write as the square root. Like so. And there's your answer. Let's talk just a little bit about the change of base formula. Suppose that b is a positive real number such that b is not equal to 1. In other words, we want it to be a base for an exponential or a logarithm. If x is any positive real number, then log base b of x is equal to the natural logarithm of x divided by the natural logarithm of b. Or, if you prefer, log base b of x is equal to the common logarithm of x divided by the common logarithm of b. In fact, the base that we're using here I'm using a natural log, which is a log base e, and here I'm using the common log, which is log base 10. But in fact, it doesn't matter what base we use for the change of base formula. If a was any base, so it was a number of which was positive and not equal to 1, then log base b of x is log base a of x divided by log base a of b. It doesn't actually matter what base a you choose, but it's convenient to just use a standard base like 10 or e. It's especially useful if you're using a calculator that only allows for base 10 or base e logarithms. So if you have a logarithm in a different base to compute, you can convert it very easily. The way that I remember this, log base b of x, the b is down further. It's written below the x. So that's why the ln of x is on top and the ln of b is on the bottom. X is higher up, so it ends up on top. B is lower down, so it's on the bottom. That's not a proof of why that's true. That's just how I remember it. That's a little mnemonic that helps me remember it. The reason the formula is true is because of this fact. This is just the cancellation law again. A raised to the log base a of b will give you just b. It's just the cancellation law again. And that's really why this is true.